Hi students, in this fourth module of electricity and magnetism, we are going to discuss about electric field and electric potential energy. Let us observe the clipping carefully. There is a positive charge, there is a negative charge, assume. Now, let us observe the electric field, how the electric field lines were formed. The lines, they are not really lines, we assume like that. It is a universal assumption for this electric field lines. Now, able to observe the clipping now. From positive charge, the lines will come out and they do reach the negative charge. Always, please remember, electric field is from positive charge to negative charge. It indicates. Now, if you observe that clipping, this positive charge and negative charge, they are much attracting in nature. They are sharing the lines also. Able to observe them. They are attracting in nature. They do attract. Now, let us consider both the positive charges. Or else you can consider both the negative charges also. Here for the example's sake, we are going to take both the positive charges. I mean like charges. Like charges, they do repel. Let us observe the lines now. Able to understand? Yes. Of course, they are very nice clippings. You might have understood well. Now, here, electric field lines are always from positive charge to negative charge. If we bring any two opposite charges nearer, they do attract. If we bring any two opposite charges nearer, they do attract. Accordingly, the field lines will form. Accordingly, the field lines will form. Like in the first clipping. Explained in the first clipping. If we bring any two same kind of charges, they do repel. Accordingly, the field lines will form. Explained in the second clipping. Now, between any two charges at some location, how to find the electric field? Between any two charges at some location, how to find the electric field? The topic is. Let us observe the explanation. Let us consider two charges first of all. Yes, again, there is a positive charge, there is a negative charge. Already we know how the electric field lines will form. Let us consider a line. So here, the electric field line we are considering. So at some place, we are going to find the electric field. Where? At the location of the point. I mean, there is a small dot. At that location, we are going to estimate the electric field. See, there are two charges given. There is a location given. Of course, there is a field line. There is a positive charge. At the location given, with respect to positive charge, yes, there is electric field. Already we learned in the previous module. Let us suppose that as E1. Here, the electric field is away from the positive charge, isn't it? Hope you remember that. Similarly, with respect to that negative charge, there is one more electric field, that is E2. But it is directed towards the negative charge. Electric field because of negative charge is towards the negative charge. Now, for this E1 and E2, there will be E net, resultant of electric fields. That is represented by E net. Of course, in the diagram, very clearly you can observe that E net is nothing but a tangent. In tangential direction, it is executing the electric field. It represents the tangent direction on the curve. What is the curve here? Electric field line. Now, at any point, the net electric field is the resultant of all the fields available at that point. Once again, at any point, the net electric field is resultant of all the fields available at that point. But please remember that the summation must be vectorial summation. Never it could be numerical summation. I mean scalar summation. The summation of electric fields must be vectorial summation. Now, just for the example's sake, on the vertices of a regular hexagon, if six identical charges are placed, then at the center of it, what is the electric field? Let us observe the diagram once again. Yes, there is a hexagon. It is a regular hexagon. I mean, with all equal sides. Now, there are six identical charges. Please observe the diagram carefully. There are six identical charges. Identical means same in quantity, same in nature. So at the center, we are going to find the electric field now. Let us observe the charge wise. There is a charge A. With respect to this assumed positive charge, with respect to this assumed positive charge, the electric field is away from it. There is an electric field with respect to A. Similarly, quite opposite to that A, there is one more charge, D. So with respect to D, there is another electric field, but it is quite opposite to the previous electric field. Both the fields are same in magnitude but opposite in the direction. Both the fields are same in magnitude but opposite in the direction. So these two fields, they do get cancelled. Of course, we will check it out in the calculation. Now, similarly, consider B charge. With respect to B, away from B, at center, there is an electric field. Quite opposite to that B, there is E. So with respect to E, there is one more field. This pair of fields will get cancelled. Similarly, once again, there is charge C. With respect to charge C, there is field. Quite opposite to that C, there is F. With respect to F also, there is field. This pair also get cancelled. So it is a simple trick that very easily one can say that the net field is 0 because all the pairs were getting cancelled. When we consider the vectorial summation, of course, if it is a numerical summation, you should take the total. As it is a vectorial summation, we are getting the result 0. So, net electric field E at the center is 0 is the conclusion for that example. But here, there is one more note. You can remember it as a note. Similarly, net electric field E at the center of a charged ring is 0. Similarly, net electric field E at the center of a charged ring is 0. Proof is after learning Gauss law. I mean, in the coming modules. After learning Gauss law, there will be so many shapes given to you where you can find different electric fields with respect to the distributed charges also. Now, electric potential energy. Now we will discuss in brief the electric potential energy. Please remember, in so many modules you will be getting so many contexts. There will be particular modules for the complicated examples also. Need not worry, you will get the complete subject. But here we are going to discuss about electric potential energy. What is electric potential energy? Now the thing is, yes, imagine two charges kept at some distance. They may repel or they may attract, depending on their nature. We are not bothered about whether they attract or repel, but they are associated. For the repulsion or for the attraction, they must be having some energy to perform it, isn't it? So, here is a conclusion that any pair or any set of particles or any set of charged particles, any group of charged particles will be having their own potential energy. Now, here we are considering two charges Q1 and Q2 separated at a distance r. Separated at a distance r. See, let us observe now. If you simply release the particles like that, of course they do repel. They start moving away. They start moving away. Why? By using what energy they are repelling with each other? By using the already assigned potential energy. That is potential energy. For any pair of charges or for any group of charges, there will be assigned potential energy. Here, charge Q1 given, charge Q2 given, they are separated at a distance r. Now, electric potential energy is the energy associated when the charged particles are together. When the charged particles are together. When the charged particles are separated, there is no matter of energy. When the charged particles are together, they possess some potential energy. Of course, very simply we can assess what is the electric potential energy by using the awareness of general mechanics. Of course, it is not a classical definition, but a simple trick. Electric potential energy, U electric. Of course, whatever be the energy, it is the energy. What is the energy here? Simple. Work done while the association. What association? Association of that two charges. While bringing that two charges together, the experimenter is doing the work. When the experimenter is doing work, while bringing that two charges, the charges gain some energy, isn't it? So that assigned electric potential energy is equals to work done while the association. That is equals to force into displacement. Force into displacement. Of course, what is the force here? K Q1 Q2 by R square. What is that? That is Coulomb's law. Force into displacement into R. Force into displacement. So finally, we do get the answer K Q1 Q2 by R. So here is the conclusion. Electric potential energy of any two charges Q1 and Q2 separated at a distance R is K Q1 Q2 by R. But let us observe this definition now. Of course, the previous definition is a trick, but here is the definition. What is the electric potential energy? See, there are two charges given. There are two charges associated. Where from they are? The scientist or the experimenter will be in a supposition, will be in a assumption that they are from infinite places. From infinite places, when you bring two charges and kept associated, there arised energy. That is the classical definition of the potential energy. Let us read it now. Electric potential energy is the energy associated when the charged particles are assigning together. That is, it is a supposition that the experimenter is bringing the charges from infinite places to get associated at a particular distance. At a particular distance. Where from the charges? From infinite places. But the experimenter is bringing that two charges associated. Now, let us observe the narration given in the clipping. Now here, there is a charge. There is an initial charge. Let us assume. Let us consider a line. On the line, we are considering a point, isn't it? On the line, we are considering a point. What is the purpose of taking point here? Yes, we are going to bring some other charge to that point. Of course, the process of association. Now, let us bring the charge from infinite places. Where from? From infinite places to that location. Where is that location? It is only at a distance r from the first charge. It is only at a distance r from the first charge. Yes, there is a charge from infinite places to that point. Here, there is an argument arised. Of course, both the charges are positive. We are taking like that. To get the two charges associated, one has to do work. The experimenter has to do work because the positive charges, they never associate. They always try to repel. Somebody is bringing that charge from infinite places to that point. You should get a doubt here. If they are of opposite in nature, there is no need of bringing. In that case, in reverse, we do define the work done. How? If one is a positive charge, if one is a negative charge, we should evaluate, we should calculate the net work done by detaching that, because already they will be in attraction. Already they will be in attraction. Now, from the first charge to the required position, the distance is r. Do say. Now here we are going to find the potential energy of these two charges separated at a distance r. So what is our purpose here? What is our purpose here? To find the potential energy of these two charges separated at a distance r. Now, so consider, very simply consider that distance as r. Yes, there is one more distance. You should note it down. That is infinite. See, where from that second charged particle? That is from infinite places. That is from infinite places. Now, on the line, on the referred line, let us consider a random distance, or else what do we can say? Random displacement. That is S. What for S we are taking here? We are going to find the work done. What for work done? To find the energy associated. To find the energy associated. Here the displacement is yes, we are going to take. So to apply the integration and differentiation in classical physics, we need ds also. So there is a small displacement. Of course, the second particle is from infinite places to this location. So in the middle, it is traveling from one dotted line to another dotted line whose gap is only ds. In that ds, what is the work done? Now, in general mechanics, already we know that work done is equals to force into displacement. Work done is equals to force into displacement. So here a small work for that ds gap. dw is equals to force into ds. Force into ds. Please remember here the force is repulsive. Against repulsive force, the second charged particle is moving. The displacement is, the displacement of the second charged particle is from right hand side to left hand side. Just now we observed that was moving. But the force there is from left hand side to right hand side because it is repulsive force. Now, what is the energy then? Electric potential energy. Electric potential energy is equal to minus of, very simple, F is kq1 q2 by s square. F is kq1 q2 by s square, the random displacement. For s, we are applying the force formula according to Coulomb's law. So kq1 q2 by s square into ds is the displacement. But here all of a sudden we are getting minus sign. Why? The minus sign is because force is repulsive. That is rightward. On which? On the second particle. On the second particle, the force is repulsive. That is rightward. But the second particle is from infinite places to that point. The movement is left side. So force and displacement, they both are in the opposite direction. Now here, force and displacement, they both are in the opposite direction. So here we are taking minus sign. Minus integral of kq1 q2 by s square into ds. Applying the limits. In applying the limits, you may be getting a doubt that smaller thing must be the lower limit, higher thing must be the upper limit. No, it's not like that. Where from the particle is? From infinite places. That is the initial limit. To what distance it is located, it is positioned at r. That is the final distance, final limit. Initial limit and final limit. So infinite to r. So electric potential energy is equals to minus of kq1 q2 by s square into ds between the limits infinite and r. That is equals to kq1 q2 minus of kq1 q2 into minus 1 by s. Of course, kq1 q2 are constants, minus is as it is. So here the integral is for 1 by s square. 1 by s square, integral is minus 1 by s. In the integrations, you may be knowing that. So minus 1 by s between the limits infinite to r. Now, applying the limits. In applying the limits, usually what do we do? throwing upper limit minus throwing lower limit. But here inside the bracket there is the term minus 1 by s. Eliminating this minus sign, you can apply the limits lower limit minus upper limit. So u is equals to minus k q1 q2 in bracket 1 by infinite minus 1 by r. Of course 1 by infinite is 0. Finally you will be getting the answer u is equals to k q1 q2 by r. U is equals to k q1 q2 by r. This minus and minus sign inside the bracket, they do get cancelled. So finally you will be getting the answer u is equals to k q1 q2 by r. See, in this example we did this derivation by taking positive charges. Both are positive charges. If one is positive and the other one is negative, what will happen? Nothing will happen. In place of q1 and q2, you will be taking their corresponding signs also, because it is a scalar quantity. It is a scalar quantity. So electric potential energy is a scalar quantity. Its unit is joule. Hope you all understood well. All the best for your preparation.